Hello, this is my screencast. When I first introduced chapter 14, I mentioned static pressure using E and B fields, and that resulting in the Poynting vector. We're also going to find Maxwell stress tensors using the same concept of E and B fields. And we are going to use it by finding a force density. So what type of force do we know of that uses both E and B field? That's the Lorentz force. Lorentz force we know is equal to QE plus QV cross B. We take the derivative with respect to volume and we get D per D volume times force, so force density. Let me step back. Before even doing so, I said Q times V is equal to Q times dx over dt is equal to current, just to get a few things cleared up. Now we have taken the derivative, and that yields a force density equal to the changing E field per unit volume plus D over D volume times the cross product current cross with B. And I said di over d volume is just current density, which we know is equal to J. Additionally, we also have Q per unit volume, which is charge per unit volume, which is rho. Rho is equal to, with the substitution of Gauss's law, is equal to E times the divergence, epsilon times the divergence of the E field. Additionally, current density is equal to the replacement with Ampere's law. I turned it around a little bit to equal J. So it is the curl of the magnetic field minus changing E field with respect to time. Just a changing E field. So after the Gauss's law replacement, we have Gauss's law and Ampere's law replacement, we have force density equal to divergence of E times the E field plus curl of B minus, quantity curl of B minus changing E field crossed with the magnetic field. So this distribution here, this dE dt cross with B, that one in particular, that can be changed up a little bit to be a little bit cleaner and to give us something a little bit more symmetric in the end. So dE over dt crossed with the magnetic field is equal to, by a substitution of a formula in the back of the book, not the answer section, the reference section, is equal to d over dt times E cross B, which is the new one I introduced at the beginning of chapter 14, which is Poynting's vector, S, minus E cross the changing magnetic field. And we know the changing magnetic field to be Faraday's law. A changing magnetic field results in an E field. Now we have force density equals Gauss's law replacement, divergence of E times E, plus magnetic field. We never changed this one. We kept it how it was, a curl of B cross with B. So we have B cross the curl of B minus E cross curl of E minus the changing Poynting vector. Now, let's go over to the other side of the board, because those E cross curl of E's, we have two of them and they're a mess. We don't want to deal with that. So let's turn this into something different. I'm not going to say it's easier, but it's different. So now, using the back of the book again, the reference formulas, it's put in terms of A and B. However, our A and B are both the same. So I just worked this out in terms of E. E cross curl of E equals grad E dot E, which would be AB, whatever, minus 2 E dot del times the E field, minus E cross curl of E. Again, so we have two of those. One's on the either side of the equal sign. After combining like terms, we have 2 E cross curl of E's equal to grad E squared minus 2 E dot del times the E field. Divide by 2 to reduce the number of coefficients we have, and we get E cross curl of E equals 1/2 grad E squared equals E dot del times the E field. Now, that's the same thing that happens to the magnetic field also. That's the same math that happens with the magnetic field. So in the end, we have a force density equal to divergence of E times the E field plus the E dot del times the E field plus del dot B, which is 0, but I put it in there just for symmetry, plus B dot del minus 1/2 grad E squared plus B squared minus the changing Poynting vector with respect to time. This is all in terms of E and B. But wait, there's a Poynting vector in there. But Poynting vector is E cross B. So that's what leads us into Maxwell tensors. I will be coming up with the second webcast, and we will discuss it further. Thank you very much, and you have a good day. Hope it wasn't too long.